so we had just in section 1.6 now, on Friday we had polynomial equations. What other equations did we have? Polynomial, radical equations, and then we had one more. Right, equations with rational exponents, right. So now those are just 3 types of equations. Prior to Friday, you had linear equations with fractions in the denominator, right? You've had rational equations and all of those quadratics. And there's like 3 different types of quadratics you can really have, but you know, they all come under quadratics. So what I would suggest as a study guide is for you to list, after today's class, all the different types of equations, because today we're going to add a couple more to this list. And then in the middle, what you should do is you should put an example of each of those types of equations, right? Just put an equation up like a polynomial equation. You could do the one from your homework up there. I'm just using this as an example. Okay, so there's an example of a polynomial equation. Oops, this is supposed to have an X there. Okay. Then over here, you should put the steps. So you got to give yourself lots of space here. A lot of space. Okay. Steps of how to solve that. Okay. Now that's like a beautiful like first page of your study sheet that you can bring in on Friday. You can do 2 sides of an 8.5 by 11 piece of paper. But if you have an example of all the different types of equations that we've solved and how to take just one and how you solve it with the steps and strategies. Another thing you might just want to put down here is, how do I recognize whether I have a radical equation or a polynomial? Whatever makes sense to you. Then the back side, the flip side, you can put whatever else you want on there. So this is something that will be hard if you try to do this like the night before or the morning before the test. So you may want to just start working on this. You can actually start taking examples right off your lecture notes if you want, or from homework or your book. Okay, so this is a little study guide suggestion, cheat sheet. Right? The cheat sheet you get to bring in. One of my students last semester had the most elaborate study sheet I've ever seen, and she did this almost for everything. But she typed it out, she used different colors. It was unbelievable what she did. I couldn't believe it. She must have been, and well, she got A's, so maybe that was part of it. Yeah. This thing here? Equations with rational. That was the last type you did on Fridays. Okay. Okay. All right. So let's finish off section 1.6, and then we're going to do 1.7 today, but all we're going to focus on in 1.7 is linear inequalities. That's it. Okay. The projects will be handed back on Wednesday, I hope, and your exam will be on Friday. Okay. So let's take a look at our next type of equation here. Oh, I got it to auto hide now. So Nathan, you want to start us off?
Today we are going to continue our work with special category equations.
It should be R. There's an R missing there.
So the question of the hour is, what do equations that are quadratic form? Examine the equations below to see find patterns that help us.
Okay, so your first job is to look at the equations on the left-hand side, which we say are quadratic in form. And you can see on the right-hand side, I have a similar quadratic equation. And see if you can find patterns so that if you're looking at the left-hand side, you'll be able to categorize this as quadratic in form. So take a few minutes and see what you come up with between everybody at your groups. So what observations have we noticed? What patterns? So if you were looking at this, say on an exam, if you were looking at this first equation, what are going to be the little signals that say, ooh, this looks like a quadratic. It has the same form of a quadratic. Notice I took this equation and wrote it as a quadratic over here. So what makes the stuff on the left side, what patterns did you notice? And I'll take as many different answers as you want to tell us. Brendan?
The exponents.
Okay.
Quadratic equation minus exponents.
Okay, so if you're looking at this, that's not the highest exponent there isn't 2. Right, so you need to find the pattern, okay, that makes it look like quadratic. It's not quadratic. This is not a quadratic equation. So let's establish that. It's not quadratic because it's a 4th degree equation, right? Highest exponent is 4. So can I just finish with Brendan? So Brendan, what you want to tell me a little bit more what you were thinking there with that idea?
Well, it didn't come from 2 factors in the quadratic equation.
So it hasn't been factored, okay. But I'm still looking for the pattern that you see here, that you also see on the other side. That's true no matter which side you're on. And you can't say the highest degree is 2 because this has a 4 and this right side has a 2. Tiffany, what did you notice? Substitution, that's fancy. Okay. Oh, you read it. So see? So Tiffany is doing what I'm suggesting on the end of every single class note, which is to preview the next section. So we're using a substitution. Yep, that's going to be how we do it. That's our strategy for solving. And Tiffany looked ahead. But suppose we don't know anything about substitution yet, and we're just looking at these, finding the pattern. Haley? They all have 3 terms, okay. They all have 3 terms. So the examples I gave you all have 3 terms, right? What else? How are you going to know from looking at the left side that it can be made into the type of problem like the right side? Julia? They're all equal to 0, yeah. Anything else that's going to give us a clue? So I'm going to put an equation that doesn't have this format that actually satisfies these 2 ideas so you can see the difference. Okay, that has 3 terms, right? This red equation has 3 terms. It's set equal to 0, but it's not quadratic in form. Orlando?
You might know it says quadratic equation slash second degree polynomial equation. Quadratic equation only go to the second degree.
Quadratic equations only go to the second power, yep. Sonia? Yep, well, on this side is the ABC. Yep, and that's what we said, but here's 3 different terms, but this is not quadratic in form. So this is not quadratic in form. There's something very special about the ones on the left side that we call them quadratic in form. It doesn't have to do with the number of terms specifically in the fact that it's set equal to 0. It's true that they all are. Logan? This can be solved with the quadratic equation, not as it's sitting there right now, but it's true we will be able to at some point. Nathan?
The one on the top left, the exponents are double exponents.
Okay, so Nathan's noticing a pattern. Something to do with the equation on the left is something to do with doubling the exponents on the right. So let's take a look at that. Okay, let's take a look. So the highest exponent we see here is what? And what is it here? 2. Is that 4 double 2? Okay, highest exponent here? Excuse me, next exponent 2. What is the exponent here? And what's the exponent on a constant? No, because then it would look like that. 0, it's x to the 0. And what happens when you double 0? 0. So that works. But within the actual equation itself, whether you're looking at quadratic or quadratic in form, there's another pattern. He's partway there. Cecily?
The ratio of the exponents is 2 to 1 to 0.
Right. So in other words, this exponent is double the middle exponent, right? Always. See here, we never put that 1 in here, but this is a square and that's a first power. So the first term, the degree of the first term is twice the degree of your middle term. Now let's look in here. The degree here is 2, the degree here is 1, twice the middle. Now even with fractions, even though it looks scary, this power is 2/3. Is that twice 1/3? Yeah. So quadratic in form has to have this pattern that if you look across you set your equation equal to 0, and then you look at the degree of your first term. If that degree is twice the degree of your middle term, it's double, then it's quadratic in form. And we're going to take a look at a strategy today. Now, it took a little while to get that out, but it's more important that we get it from you than it is for me to just tell you, okay? So part of taking any type of assessment is for you to recognize what type of equation you have first, and then you pull from your memory or your notes, your cheat sheet, the strategies to solve. So let's take a look at how we're going to solve this. Now we're going to be able to turn this in to an equation that looks like the right-hand side. And the way we do that is with something called substitution, which is what Tiffany was talking about. So let's take a look. And this is a really good strategy to use often in lots of different ways in mathematics. So we notice this first equation is a 4th degree equation, so it's not quadratic. Okay, it's not quadratic as it's sitting there. We're going to make it look like it. We're going to do a little plastic surgery to it, okay, to make it look like a quadratic, but it's always going to be the same equation underneath. It's going to be a 4th degree equation. Now, remember what we talked about. If you circle the highest power, that tells you how many potential solutions you could have. So how many potential solutions could we have for this equation? 4. So we may have 4 potential solutions in our solution set. No. Just like with the quadratic, did Cecily ask that? Megan, with a quadratic equation, you could have 2 if it goes through the x-axis twice. You could have once, and sometimes it doesn't go through at all. So it's always the maximum. It's your potential maximum number, right? So this is your maximum number, but it doesn't mean you'll have 4. Okay? Yeah.
So what about for one of them,
No, because you can't have 2/3 of a solution. So it's a good question. When it's a polynomial equation, that one is not a polynomial because it's not an integer or non-negative whole number. Okay. I shouldn't say integer because integer would put something in the denominator, right? So it's a non-negative whole number. These are all non-negative whole numbers for the degree. That's considered a rational exponent equation. So that doesn't hold. So this idea, thank you for clarifying that, is only when you have polynomial equations. Okay. So what we recognize here, and this is what, who came up with this idea about the 4-2 doubling of the exponents? I forgot already. Not Nathan, it was who spoke after Nathan. Cicely, okay. So notice we can take the middle term, which is x squared, right? And if we square x squared, we get the first term. We rewrite the second term just as itself. And now, if you use this idea of substitution, you let a letter. Your book uses U, little baby U. You can use any letter you want, like big capital A. You could use a smiley face if you wanted. It really doesn't matter. It's a symbol. So if this is now the strategy for solving these, if you let U equal x squared, then we can rewrite the equation by replacing x squared with the letter U. So the first term is x to the 4th. We can rewrite x to the 4th as x squared squared. So then when we use the U substitution, wherever we see an x squared, we're going to replace it with a u. This becomes u squared. Okay, so let's rewrite this equation as an equation in u. So x to the fourth becomes u squared. Because remember, u is x squared. So that's the same as x squared squared, which is x to the fourth. And what does 10x squared become? 10 times u, right. Because we're replacing x squared with u. So everywhere I had an x squared, I'm going to replace it with a red u. And then we have the plus 9 equals 0. Now this equation right here, the black and red equation, looks like quadratic. Right? Looks just like a quadratic. So if at this point, Logan, if you wanted to use the quadratic formula to solve for u, you could. A is 1, B is negative 10, and C is 9. But I would suggest on this one, and anytime it's easily factorable, to factor it and use your zero product principle. So what are the factors of 9 that add up to 10? What factors of 9 add up to 10? 9 and 1. So we're going to factor this left-hand side, u minus 9, u minus 1, and set it equal to 0. Okay? And now you know this. That is negative 10 when you add the middle and outer terms. Okay? Because we're trying to make it look like a quadratic equation, Curtis. So the way to do that is to turn this fourth degree into a second degree. And the only way we can do that is to say this is equal to x squared squared. And then you see your x squares here. They both have x squares in them, right? So that's what you call u. Now I can show you another way in a minute, Curtis, that would work for this one without the substitution. Okay, so now you know the drill from here, right? You all know, I'm sure you all know what you do next. You set each factor equal to 0. You've done this 100 times already. Well, maybe 55, okay? And then you solve for u. Okay? But are we done? No, because the original equation was for what, in what variable? X, right? The original equation was in x. So we want to solve for x. So now we have to replace u. We got to go back to our sneaky little substitution and say, okay, just so I knew how to deal with this equation, I use this u idea to substitute. Now I got to go back and say, all right, time to get real, time to go back to the original equation. I want to now resubstitute what u equals. U was x squared. So I replace u with x squared, because that's what it stands for. And now look at what I have. X squared equals 9, and x squared equals 1. So I now have two what? Two baby quadratics. Now I call them babies, but remember, these are the baby quadratics that often can get you in trouble. Excuse me. How many potential solutions do we have? 4 from the original equation. When you look at this, I'm telling you, based on my experience, the best way for you to solve this is to subtract 9 from each side and to subtract 1 from each side and factor so you see a 2. Because if you do that square root, you're just going to say x is 3 and x is 1. You're going to forget. Right? So you got two choices here. You can say x squared minus 9 is 0. Difference of squares. Boom. I'm almost done here. I just factor that very quickly. I subtract 1 from both sides. X plus 1, x minus 1 equals 0. Now I set each factor equal to 0 and solve for x. And there are my 4 solutions. There they are. So the elements of the solution set, if I list them from smallest to largest, which is what my math lab asked you to do, they ask you to put them smallest to largest, so you put them in ascending order there. It's -3, -1, 1, and 3. So the trick here is, number 1, recognizing that you have something quadratic in form, and then using this little substitution. Now I want to go back to Curtis's idea of, well, he was trying to figure out why we use the u. But let me show you that you could have done this problem without a u. And it's important to see several different methods. If you get this one, no problem, then turn off. You don't even have to listen to me. But I do want to show you another. So let's go back to the original problem. X to the fourth minus 10x squared plus 9 equals 0. And when I see this, I think quadratic, because I see this relationship of 2 to 1, this ratio here, okay? However, you can factor that right now. If I gave you this, I'm going to cross off the 0. If I gave you that second degree trinomial on the left side and asked you to factor it, back in section P4 when you did factoring, you could say, I need factors of 9 that add to 10. It's the same thing, except the only difference here is instead of the first term in each binomial being x, it's x squared. There's my x squared times my x squared. There's my x to the fourth. I need factors of 9 that add to 10. That hasn't changed. Boom, boom. And now you have your zero product principle staring you in the face. Now you say, are each one of those factored completely? And you say, nope, because this first factor is not prime. I can factor it in as the difference of squares. And this second factor is not prime. I can also factor that. And there you go. There are your 4 solutions. Plus and minus 3, plus and minus 1. So some of them you don't even have to use this little baby u substitution if you don't want to. Okay? Well, if you can factor it easily, you probably don't have to. And when you can factor it easily, you either use, then you would use the quadratic. And remember, you would use the quadratic on your u substitution, not on your original x to the fourth. Any other questions? Okay, let's see if we got any more to look at. Okay, so let's take a look at the second one I gave you. Now, if you saw this all by yourself, sitting lonely in your room at night, sweating over your math homework, right? Your temptation here is going to be to do what? When you see something like this, what's your temptation going to be? I don't know if you're going to factor the bad boy, but you will square it, right? So your tendency, because you're not thinking, it's been a long day, your kids got, in trouble, whatever, or, your girlfriend got mad at you, or whoever, whatever, you worked 6,000 hours at work this week, right? Whatever your situation is, you look at that and you go back to what's sort of like traditional. So you don't say to yourself, oh, this looks quadratic in form because I have a second degree here and a first degree there. What you want to do is you square this and you multiply the whole thing out. Guess what? If you do that, it's okay, as long as you remember that x plus 3 squared is not what? X squared plus 3 squared, right? Before you leave 107, I will guarantee nobody in this class will be squaring each of those terms. So if you were to do this out the long way, this first one would be x squared plus 6x plus 9 plus 7x plus 21 minus 18 equals 0. And then you do all your combining of like terms and you'll get a quadratic. You can do it that way. But we're suggesting that you use a little u to substitute for x plus 3. So let's rewrite this with the u substitution. So instead of x plus 3 squared, I'm using one single letter called u. So that's going to look like this, u squared. And then instead of 7 times x plus 3, I'm going to call it u. Minus 18 equals 0. Now looking at that, okay, you say, okay, let's see here. Can I factor that easily? Are there factors of 18, and I always use the operation in front to become my action, my verb, that differs by 7. Well, let's see, factors of 18 that differ by 7. We got 18 and 1. Do those differ by 7? No. What's my next factors? 9 and 2. Do those differ by 7? Bing, 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 bing. Okay, so I can factor this to be u plus 9 and u minus 2. Okay. And now I set each factor equal to 0, u plus 9 equals 0, and u minus 2 equals 0. And I solve for u first. I solve for u. See, everything is about u. Okay, u equals negative 9, and u equals 2. But am I done? Nope. Now I have to substitute for u back to x. No, because I add 2 to both sides here, Orlando. See, add 2. Okay, and subtract 9. Okay, now I go back and say, hey, u was x plus 3. So now I go back and say x plus 3 equals negative 9. And x plus 3 equals 2. And now I solve for x, which was my original instructions. Okay, I solve for x. Okay, so when I subtract 3 from both sides, I get x equals negative 12. Subtract 3 from both sides, I get x equals negative 1. And then check your answers. I'm not going to do it. You check your answers to see if they both work in the original equation. Okay, in the original. Did anybody go ahead and check them before I got there? Ryan, I was hoping you had, but that's okay. All right, so you always want to check. Okay, let's go back and check. All right. I feel funny not doing it. So what was it? X plus 3 squared, right? Plus 7 times x plus 3 what? Minus what? Minus 18 equals 0. So let's put in negative 12, and let's see. Negative 12 plus 3 squared plus 7 times negative 12 plus 3 minus 18 equals 0. Negative 12 plus 3 is negative 9. We're going to square that. And 7 times negative 9 minus 18. Negative 9 squared is 81 minus 63 minus 18. Woohoo! 0 equals 0. We're happy. So this is definitely a solution. And now let's try negative 1. Negative 1 plus 3 squared plus 7 times negative 1 plus 3 minus 18 equals 0. So we get 2 squared plus 7 times negative 2 minus 18, right? So that's 4 minus 14 minus 18. Does that work? No. So the only solution here is negative 12. Okay? Only one solution. Yes. Yep. So I made an error, which John caught. Negative 1 plus 2 is what? Positive 2. So that's 4 plus 14 minus 18 equals 0. 18 minus 18 equals 0. 0 equals 0. So yes, this is a solution. I'm getting tricky. All right. Now, could you have, let's say you're on your test and you're feeling stressed out and you just kind of want to get a sense of your answers. Could you have gotten the answer to this equation by using your calculator? Nope, before you even solve it. Could I put this in my calculator? Oh yeah, one of those methods we talked about, right? We talked about 2 different methods. So if I wanted to use my calculator, and sometimes you will see on tests, like especially the final, if you cannot solve something algebraically, but you can do it graphically, meaning with your calculator, write down your steps and show me what you did, and you will get partial credit. Okay, so even if you can't do something algebraically and you want to try it graphically, so one of the things we can do is we can set all of this equal to y1, set this equal to y2, and then ask for the 0 command, which is when does it cross, what value of x will make y equal to 0. Okay, so you could also look on the table, yes. You can do it graphically or numerically, okay? So with your graphing calculator, you could put in I'll just do one. You could do it graphically or numerically. So let's get rid of that equation. So you need your parentheses, x plus 3. You're going to square it, right? Then plus 7 times x plus 3 minus 18. Okay? That's y1. You could use your 0 command right now, or you could use your intersect command if you do this y1 equals y2. You got two different ways to look at it. So if you set a second equation and you say y2 is going to be the x-axis, which is y equals 0, because all the values along the x-axis, y is 0, then you're going to use your intersect command. Second calc, intersect. It's going to graph it for you. You can't see what's happening up above, but you do want to. So look, we can't see. What were our answers? A negative 12. And what's the standard window give us for our x min? Negative 10 to positive 10. So we can't see our other solution. So we have to change this to say negative 15 and regraph it. Now we can see. We don't really care. We know this is going to be parabola in shape, and the bottom part of my parabola where my vertex is down below my window, but I don't care about that because I'm asking where does this hit the x-axis? Okay, and there are the two spots. So now you do second calc. You go down to intersect. First curve, second curve. Oh yeah, I got to do this trace thing, which I hate. I did. I'm going to start again. You could do either one. So let's do 0 because it's easier. All right, so here's your first place where it intersects, right? Pick a number to the left, any number. Well, that looks, I'm going to pick negative, what, 15? Right, that's to the left. And look, you don't have to play around with your cursor. You just go negative 15, like that. Boom. Now pick a number to the right, but don't go past your other x-intercept. So a number to the right would be like negative 9, hit boom. And now when it says guess, you hit boom again, and there's your first 0 right there. So the 0 command is really easy, much easier sometimes than the intersect, because on the intersect, you got to bring your cursor over. I'll get you in a minute, Megan, I see you. Okay, so you take a little, oop, I wanted to take a picture of that. What happened? Okay, let's take a little picture and put it on. So this is just, you know, in dire straits. When you're in dire straits and you can't do the algebra, this is a way of at least coming up with some reasonable answer that you could put on your test, as long as you tell me. Don't just write the answer and think you're going to get credit, because if you don't show your algebraic work, you won't get credit. But if you did this, drew a picture and said, I used my calculator and I put this in y1, this in y2, and I used the 0 command, then you will get credit. Okay? So, Megan, you had a question. Right, I only did one. Here's your other negative one right there. Okay, I only did one just to save time. Okay, all right. All right, so I'm going to skip this one for now because I want to move along. It's already 20. We'll come back to this. This is exactly the same, folks, as the two we've just done, except for now you let u equal x to the 1/3. So you get rid of all of those ugly fractions. So this becomes 5u squared plus, that should say 2/3, does it? Yeah. Plus 11u plus 2 equals 0. And then you need to factor that. I'll do it. Let's do it. So u equals x to the 1/3. Now, factors of 5 and 2 that add up to 11. Well, 5 and 1 and 2 and 1, both those numbers are prime. So 5 times 2 is 10. 1 times 1 is 1. So this is going to be something you could factor. 5u times u is 5u squared. The 5 multiplies the 2, so the 2 goes over in the other factor, and 2 times 1, plus and plus. Okay, now we use our 0 product principle. 5u plus 1 equals 0, and u plus 2 equals 0. So u equals negative 1/5, and u equals negative 2. So now we go and we've set each factor equal to 0, but we're not done. So we take u and we go back and we substitute x to the 1/3 equals negative 1/5, and x to the 1/3 equals negative 2. And the reason why this particular section is nice is it gives you a reminder of how to solve all types of equations in the end. So now we have a rational exponent equation, right? An equation with rational exponents in it. And what was our strategy? We wanted to make, oops, that should say x to the 1/3, not u. So we want to make this x to the first power. So what power do I raise this to? What exponent? So I get x to the first? No, if I raise it to the 1/3, I'm going to make that 1/9. Sonia? What does this say? If I wrote this as a radical, what radical would it be? Nope, there's no 1 over anything. This just says the cube root, right? How do you undo a cube root? You cube it, right? So if you cube this and you multiply 1/3 times 3, 3 is the reciprocal. Some of you haven't done this homework yet, I can tell. That's okay. Okay, so you cube each side and you get x. X equals negative 1 over 125, and x equals negative 8. Okay, so to undo your rational exponent, whichever one it is, even if it had a 2 there or a 5 there, it doesn't matter in the numerator. You raise both sides to the reciprocal of that power, whatever it is. Sonia? Yes. Flip in the fraction, flip in the exponent. That's what. Okay, that's fine. That's your action, but the name of it is reciprocal. So if reciprocal's not in your vocabulary yet, folks, that might be a nice little thing to add to your vocabulary glossary you're keeping. Is Tiffany the only one in the class keeping a vocabulary glossary? Mm-hmm. Good. Your for your copy? Okay. Okay. All right. Our last type of equations we've actually been solving already without knowing it when we've been taking the square root of x squared on both sides of our equation, and we end up with an absolute value. So let's use our graphing calculator to solve the absolute value of x equals 3 by letting y1 equal the absolute value and y2 equal to 3. So let's go to our calculator. So let's remember where the absolute value is. Does anybody remember where the absolute value is? Math, num, and there it is, ABS. Bless you. Okay, so the left-hand side of my equation is absolute value of x. That goes in y1. The right-hand side is 3. Okay, we're going to copy this graph. I'll keep the standard window. I don't, the standard window is probably good enough. There it is. Okay, so there's my standard window. I don't know why every time I go to use this. Look at your equation, absolute value on one side and 3 on the other. Okay. So notice we have 2 different equations, and we're going to be interested in where they intersect, right? Where they intersect. Okay. But you can look at this and okay, folks, okay? All right, so we're interested in where these intersect. We can find that with the intersection command, or we can just look at our graph here fairly easily. What are the x values where these 2 intersect? -3 and +3. Right here at -3, the value for both is 3, and at +3, it's 3. Okay, so we have 2 numbers. We know this already. And this is why we use this when we're solving a quadratic equation that looks like this. Anytime you have a quadratic equation where you have x squared equals a constant, we know if we take the square roots of both sides, we get the absolute value of x equals the square root of that constant. And prior to today, we've been saying that thing inside of the absolute value could be a positive square root of c or a negative square root of c. Okay? So this is just backing that up, that when you have an absolute value equation that you're trying to solve, and it has this form, whatever's inside the parentheses is equal to a constant, then you take whatever's inside the parentheses and you say it could be positive c, or whatever's inside of the parentheses could be negative c, because we know that if we replace u with c, the absolute value of c is c, and the absolute value of its opposite is also c. Because the absolute value of opposites are the same distance from 0. And that's what absolute value tells you. So here's c, here's the opposite of c. They have the same distance from 0. That's the absolute value. Okay? So let's see how we would solve an equation that has absolute values around it. Okay, so here's our given equation. And if you want, you could do the substitution thing here. You could say let u, or let u equal 2x plus 1, and just solve that as absolute value of u equals 11. So the stuff inside u would equal positive 11, or the stuff inside would equal negative 11, and then resubstitute. This substitution idea is a great strategy in algebra throughout any class you take from this point on. Okay, so let's rewrite this without the absolute values by setting the stuff inside. I always call this the stuff, like we're stuffing a turkey. Okay, the stuff inside could be a positive 11, or the stuff inside could be a negative 11. And it doesn't matter, because the absolute value of positive 11 and negative 11 is 11. So you take the stuff inside. There's your stuff, right? Here's your stuff. So you write two equations with your stuff. So you always write two equations that has the stuff involved in it. Whatever that stuff is. I'm not doing anything to the stuff except for creating two new equations. What can that stuff equal? That stuff could equal a positive 11, or it could equal a negative 11. Okay? So you just take the stuff out and you set it equal to a positive, whatever that constant is, and its opposite. And then you have two baby linear equations to solve, as you always have learned how to solve them. So you get 5, and in this case you get 2x equals negative 12, x equals negative 6, and then you got to check. So you go back to your original equation, 2 times 5 plus 1, absolute value of that 11, yep, 11 is 11. Smiley face. Go back and put a negative 6 in. 2 times negative 6 plus 1. We get negative 11. Perfect. Absolute value of negative 11 is 11. I'm happy. Life is beautiful. Okay? So absolute value equations are not difficult to solve. You just got to remember that whatever's inside could be equal to two different constants. One is positive, one is negative. Yep. I don't know. I haven't made it up yet. If I say, give me an example of a rational exponent equation, then you need to know what rational exponents are. If I say, give me an example of two factors, you need to know what factors are. Okay? So you need to know language. We use it all the time. That's right. That's right. Okay, so let's take a look at this one. This one looks a lot like, can we not talk about or focus on the test right now, folks? Thank you. I don't want anybody to become anxious in class until Friday. And I can't do anything about your anxiety, because I had it all the time too. I could never get rid of the anxiety for taking tests. Okay, I did well on them, but I still had the anxiety. All right, what do we want to do? Isolate, isolate, isolate. Isolate the absolute value term. How did that switch to black? That was really interesting. Look at that, right in the middle of writing. Huh. So here's our absolute value term. Remember, terms are the addition, parts of addition and subtraction. So we want to get this all by itself. So I'm going to subtract 4 from both sides, just like I would do if that said 3x plus 4 equals 25. Okay, I'm going to isolate it. I will eventually. So I'm going to subtract 4 from both sides. Okay? This is always my first step. Right now, who asked that, Nathan or Logan? Oh, Ian. I wouldn't want to divide everything on both sides by 3 because then I would have 4/3 and 25/3 and I'd have yucky fractions. Okay, so I always.
Oh, I just meant after that.
Yeah, well, I haven't gotten there yet. Okay. Now to isolate the term, we know that not only does it have to be by itself, but the second step is to get a 1 as the coefficient. That's the thing multiplying your absolute value. So in order to undo the multiplication of 3, I have to do its inverse operation, which is to divide both sides by 3. And I get 2x minus 1 equals 7. And now I got my stuff inside. What's my stuff inside? 2x minus 1. So I create 2 equations using my stuff. And I'm hot stuff today. Here we go. 2x minus 1. There's my first equation. Not yet. I'm getting there. There's the second part of my equation. I'm almost there. And what does that stuff equal? It could equal a 7 inside there because the absolute value of 7 is 7. But it could also equal what, Liza? -7. And there's your 2 baby linear equations to solve. 2x equals 8. X could be 4. 2x equals -6, x could be -3, and it's up to you to check to see if both of those are in the solution set. Okay, so that's absolute value equations. Okay, I think if you just try a substitution, you could see how that substitution could help you start to solve your equations, so then you can feel comfortable. If they're both in it, then yeah, you should do this, yes, because that's what you'd have to do on my math lab. But if you don't do that on the test, I'm not going to take off. Are we good? Any questions? All right, so now we'll hit. You can find a neighbor later and discuss 8. I want to make sure we get linear inequalities in. Okay. So here, that came out funny on my screen. How's that look on your paper? Came out? Oh, so I lost my number line. Boo. I'll get one. Now, for those of you who weren't here early, I mentioned that Class 9 notes are on this packet. And guess what? Class 9 was also on last week's packet. It's the last class before your study guide. I've forgotten I had it on 9, so you have it in 2 places, on this packet and on last week's packet. They're identical, yes. I just reprinted it by accident. So mea culpa, I wasted a few pages of paper, and I always feel badly about that. Okay, so for some reason, this number line didn't come out when I changed this over. So it says, how could you represent the solution to this inequality? And I gave you a hint. You could represent it with a number line, right? With a number line. So how would I write x less than or equal to 7? Someone want to tell me? Julia? I circle it and fill it in because it's included with the equal, and then what do I do? Arrow to the left. That's your solution set. Okay? If we use set builder notation, we always start set builder with our curly braces like that, and we say it's the set of all x such that, and then you put your inequality in there. There you go. That's set builder notation. Well, lo and behold, we're finally getting there. We have another notation we can use, and I've been waiting to cover this for, what class is this? For 9 classes, because it's much quicker to use. It's called interval notation. So to represent what you see on the number line and what you see in set builder notation, all the numbers less than 7, you say, Well, what would be the number to the left if we kept going on this arrow? Well, there is no number because it continues on forever and ever, but we refer to that as infinity and the direction is to the left, so we call it negative infinity. So because negative infinity cannot be represented by a single number, we use parentheses, and that indicates that it's not included. Use a parenthesis to say you can't include negative. I'm going to show you. I haven't gotten there. Can I finish? Okay. I haven't finished my discussion of this yet. So after I'm done, then you can ask me why there's a bracket on 7. Okay. So then you go to the right, and what happens when you get to the right? Boom! You run into the number 7. So then you put a 7. But when you want to include all of your papers to hand in to me, you can use a staple, right? And what does a staple look like? It looks like a bracket, right? And are we including 7 in our answer set? Yep. So since 7 is included, I use a bracket. And that tells me, hey, 7 is part of this solution set. Right. If 7 was not part of it, then you would say, I'm open. I'm a parenthesis. Okay. So that's interval notation. 7 is part of the solution set, so you use the bracket, not the parentheses. Okay? And I got a few here to help you practice this. Okay. So here you go. You don't like those, but with a little bit of practice, folks, anytime something is new, if you give it a chance, you might find it very convenient to write instead of set builder notation. So what would this represent? 2, 3 with the brackets. Just be 2, not just 2 and 3. You fill in the 2 and 3, and it's all the numbers in between. Remember, we now know numbers other than integers. So that's an infinite solution set. There's an infinite number of numbers between 2 and 3. So it's not just 2 and 3. Okay? So the square brackets tell us that. What about if I have parentheses -1, 5, and I was on the number line? Do you have number lines at your seat? Yeah, these are the number lines right here. They got to be vertical, I guess. So -1 and 5, what would that look like? Open circle at -1 because it's a parenthesis, doesn't have a staple, and 5 has a parenthesis and everything in between. So it represents all the numbers between negative and 5, but not -1 and not -5. Okay, the next one we have parentheses -4 and bracket +1. So we go to -4, we put in little ticky, and then we go to 1. And then what do I do with the 1? Is that included or not included? Yeah, the staple's on 1, right? The staple gun. So that gets colored in. What about -4? It's open parentheses, so that's a circle. We're not including -4. It's not part of our solution. Then everything in between gets colored. And look right above, everything I've shown you in set builder notation. So notice x is less than or equal to 1, but it's greater than -4. So you got the number line picture, you got your set builder picture, and now you've got your interval notation. Okay, so notice these two intervals here. -infinity to a, b to +infinity. These are examples of infinite intervals. Parentheses are always used anytime -infinity or +infinity is used. You always have to have parentheses around it because it's not a specific number. It's a concept. Okay? It represents an idea of things continuing on forever and ever. Okay? So let's see how we use these intervals. Well, every time we solve a linear inequality, I got to figure out why this is happening. So unfortunately, we don't have time for you to try this at your seats, but let's just go to B right here and see what this says. This says I'm trying to find the set of numbers x, and I know there's more than one number because this is not an equality here, it's an inequality. What x is, when I multiply it by -4, will I get a number less than 8? That's what it's asking. Okay, so we divide both sides by -4. and we get x on our left side, and we get -2 on our right side. But there's an important change we've got to remember. We change the direction of our inequality. So what was less than now becomes greater than. It's with division and multiplication. Anytime you multiply, because every single division problem can be written as a multiplication problem by the reciprocal. So anytime you multiply or divide both sides of an inequality, this should be not new, I don't think, to anybody. You've had this before. You reverse, change, flip, whatever you want to say, reverse the direction of the inequality. So on the number line, this is all numbers greater than -2, but not including -2, because it's a strictly greater than. So there's an infinite solution set represented here. In set builder notation, I'd have to do this. This didn't come out right either when I converted it. X such that x is greater than -2. It's fine. Nothing happens. Okay. Okay. Now, what would this look like in interval notation? Excuse me, in interval notation. Am I including the -2? No. So that's my open arms. I'm letting it go free. I'm opening up my arms. And then it goes all the way to what? Infinity. And I can't include infinity either. So this is interval notation. So I don't have to write all of this curly braces stuff, and I don't have to do a number line. That says all the numbers bigger than -2 forever and ever and ever. Right now I'm starting to sound like a priest. Okay, yep. Only when it's negative. You can add and subtract, and you can divide both sides by positive or multiply both sides by a positive, and no changes. This is the only thing you ever have to remember. When it's negative and you're multiplying and dividing, right? Okay. All right, so what happens here? Which inequality would you prefer to solve, folks? The left-hand side or the right-hand side? And this will tell me something about your personality if you say the left-hand side. If I gave you one of these on Friday's test, which one would you prefer to do? The right, right? Or you like the left? You like challenges? Okay. Guess what, folks? These are the same. And after all your work, I hope, that we've done with solving equations with fractions in the denominator, what's the LCM here of 2, 3, and 6? 6. So what are we going to do? Multiply everything on both sides of the inequality by 6. So you throw a 6 in here, a 6 in here, and a 6 in here. And what else do you remember to do? You put your arms around any binomial you see so that you will distribute that number. So we get 6 times x minus 4 all over 2 is greater than 6 times x minus 2 all over 3 plus 5, 6 times 6. And what happens? Every single denominator will have a common factor with your multiple because you've chosen it that way. So every single denominator will become 1 instead of the ugly numbers that they are now. Excuse me, I didn't mean to call 2 and 3 and 6 ugly. Okay? The ugliest number that you'll ever do. Okay? So now look what we have. 3 times x minus 4 is greater than or equal to 2 times x minus 2 plus 5. And that's exactly what you have on the right-hand side. And you solve that like you normally would, just like an equation. You use your distributive property on the left-hand side, the distributive property on the right-hand side. No like terms on the left-hand side, but you have -4 and 5, so that's 2x plus 1. You add 12 to both sides. No worries, because you're just adding. No worries to think about changing that sign. 3x is greater than or equal to 2x plus 13. You subtract, no worries when you're subtracting. And what do you get? X is greater than or equal to 13. So Liza, how am I going to represent that in interval notation? Greater than or equal to 13? No, I'm with interval, since you don't like it. You put a 13, right? Staple or open arms. That's right. Comma, and then how far do we go out? Infinity, right? And then what goes after in parentheses? There you go. See? Not too bad. All right. And I'm not going to do compound inequalities because I can't put anything else into your brain. Have a great couple of days. We'll pick up with compound inequalities, or you can look it over in your book or whatever. So I'll see you on Wednesday. Again, if you want to get your take-home quiz into me early, I'll grade it for Wednesday. Otherwise, I don't know if you've noticed, I have solutions to quizzes on Moodle. Moodle Baboodle. Ian, do you have a question? Uh-oh, hang on. I can't, there we go. I got to get this lecture up. Hang on. Okay, so the